I'm skipping a few slides here where there is discussion about the different forms of aramid fibers and PBO fibers, etc. So basically, you can look through that. I'm not going to be able to give you any more information than what is given in those slides. So let's talk. Let's now talk about ceramic fibers. Why ceramic fibers? Um, in the case of polymer matrix composites, I think I mentioned to you that when you add, the reason for adding carbon fibers is to strengthen the material. But in the case of ceramics, the ceramics by themselves are pretty strong, but they are extremely brittle. So the reason why you are adding carbon fibers or adding ceramic fibers in ceramic matrices is to toughen the material or to provide it with crack resistance and to add other forms of toughening mechanisms into this material so that it can withstand the effect of sudden impact. But carbon fibers or continuous ceramic fibers are good for reinforcing any of these matrices, but mainly they are used for metal and ceramic matrices. They also have very good environmental resistance, except that sometimes during the manufacturing process itself there could be some byproducts that are created that could react with the fibers and degrade those fibers, or sometimes the temperature of processing could be higher than the temperature that these fibers are able to withstand. So most of the time they are attractive as reinforcements in high temperature structural materials. And what do you mean by high temperature? High temperature means temperatures above 1200 degrees centigrade or above 2500 degrees Fahrenheit. Now, are there not high temperature composites in the case of polymer matrix composites? Yes, there are. There could be some like um a polyamide matrix where you have carbon fibers, um, and those could be done in order to withstand temperatures like 1500 degrees Fahrenheit or 1000 to 1500 degrees Fahrenheit, or in degrees centigrade it could be between 500 to 700 degrees centigrade. So how do you process ceramic fibers? So there are a couple of different ways to do that, and the most traditional method is by chemical vapor deposition. You could also do it by a process called polymer pyrolysis or a sol gel technique, where you take a squishy precursor and pull it through a set of dyes and dry it and heat treat that to get the high temperature properties of this material. You could also have a process where you are taking a melt of the precursor and pulling it through dyes and things like that. But that is not as common as chemical vapor deposition or sol gel technique. So when we started out, like almost 30 years ago, 25, 30 years ago, um, there was a lot of effort being spent by the Department of Defense, Department of Energy, etc., to make ceramic components for automotive applications, automotive and other high temperature applications. But very quickly they figured out that it was necessary for you to reinforce this material with different kinds of fibers. So when we started looking at silicon carbide fibers, silicon carbide matrices or silicon nitride matrices, they figured out that you had to use something that was comparable, which was the silicon carbide fibers. But it was not easy to make silicon carbide fibers by the traditional methods. So what they did was they used a substrate to deposit the silicon carbide matrix around it. So the silicon carbide matrix was deposited around a wire of tungsten or carbon heated to around 1300 degrees centigrade. And you have you take a reactive gaseous mixture such as hydrogen and uh, poly it's methyl trichlorosilane, or what you would euphemistically call alkyl silanes. Don't worry too much about the chemical structure or chemical nature of the fiber itself. I mean, of the gas itself. But just know that you are taking a highly reactive material such as um methyl trichlorosilane, which is a dangerous gas, and you are blending it with hydrogen and reacting it at around 1300 degrees centigrade. And it then deposits through a process of chemical vapor deposition on the tungsten substrate, which is approximately 13 to 15 microns. And it creates a pretty big diameter silicon carbide fibers. But now people have figured out to make these silicon carbide fibers at much smaller diameters. So this is the schematic of the CVD process, where you are reacting it in a chamber, and while the fiber is being pulled through that, and it deposits this silicon carbide matrix around the substrate. So as I said, it is methyl trichlorosilane CS3SiCl3, um, and because it has got one silicon and one carbon atom, so you can get a stoichiometric ratio of silicon carbide, and it forms a byproduct of hydrogen chloride gas. Now, what is special about hydrogen chloride gas? Hydrogen chloride gas is extremely nauseous and corrosive. So you have to protect your inside of your chamber from getting reacted with the or getting attacked by the hydrogen chloride gas. So generally you mix free carbon and solid or liquid silicon uh, with the silicon carbide itself. So this monofilament can be as much as 100 to 150 microns. And the unfortunate part is that this large diameter fiber is not flexible. So you're taking maybe like um, 100 of these filaments, pretty thick filaments, and you can't weave them. You can't do anything with that. This is again another schematic of the whole process. So these fibers used to be called SCX6. Now there are other um, technologies for making silicon carbide, pure silicon carbide fibers, um, made in Japan and things like that. So those are much more um, smaller diameter fibers are produced, which can easily be woven and things like that. So this is typically done by a uh, starting pre-polymer, which is a pre-ceramic polymer, and you melt spin the polymer into a precursor fiber, and then cure that fiber to cross-link the molecular chains, and then you heat treat that to get the right kind of structure. So these are the different steps of that. So one of these process is called the Nicolon or Yajima process that was developed in Japan. Now, uh, the problem in those days was that the silicon carbide fibers that were produced were not very pure. So you had to it did not withstand certain, and it would get attacked by the processing temperature, etc. So it was not a very good process, but now they seem to have overcome those problems, and they are producing much better fibers. And there are also other fiber manufacturers such as Silramic, and they are supplying that fiber. It's called Silramic fibers. They are being supplied through companies such as, it's called COI, that is part of ATK Orbital in San Diego. So again, this is a schematic, so if you can please go and expand it, you will be able to see that. So what are some of the advantages? So you can see this, okay? See the tensile strength of these fibers. There is another fiber called Tyranno SA3. So these are much higher Young's modulus and stiffness compared to the Nickelon or the high Nickelon or the high Nickelon S type of fibers. The advantage is that the disadvantage with the Nickelon fiber is that it does not have a very high thermal conductivity. So when you make a component, especially these high temperature components, you need them to have very high thermal conductivity. Low thermal expansion coefficient, but high thermal conductivity. So you can only do that with either Silramic or Tyranno. So these are some of the properties of the Tyranno type of fibers. So you can see that much higher strength, and the density is also pretty lower compared to the standard silicon carbide fibers. So Tyranno is made by, again, they are made in Japan by a manufacturer called Ube, and it is supplied through COI in San Diego, California. So this is the type of fabric that you get, and you can take that and make it into a composite by pre-pregging it or using it for chemical vapor infiltration, etc. So these are the different suppliers for ceramic fibers. Uh, the carbon fibers are supplied by Hexcel and Toray and Cytec, and Ube and 3M supply. Ube supplies the silicon carbide fibers, whereas 3M supplies the alumina fibers. So if you look at the Nickelon fibers, Nickelon or Nikelon, Nickelon is what it is called. You can see that the fracture initiates from one corner, so it is an extremely brittle fiber, and it radiates out into the rest of the fabric, rest of the fiber itself. So the process for making alumina or zirconia type of fibers is slightly different. So you have to use a process that is based on the sol gel process. So you formulate the sol, which is again a liquid precursor of the ceramic material of alumina or zirconia, and then you concentrate to form a viscous gel, and then you pull out the fibers, spin that, and then you cancel it to produce the oxide fibers. So these are again some different variations of the carbon fibers, the alumina fibers. I won't go too much into that. So you can see that this is the surface of an alumina fiber, and it is polycrystalline. So it's very crystalline type of fibers, unlike carbon fibers or silicon carbide fibers, etc. They are not crystalline. So you have a number of different types of alumina fibers produced by the 3M Corporation. So these are all available under the trade name Nextel, and Nextel is also used for um, things like the body suit of a firefighter, etc. So these are all Nextel 312, 440, 550 up to 720. So Nextel 312 is the most common variety. It's not a very very highly strong or highly pure form of alumina itself. It contains a lot of ingredients that reduce the strength of this fiber, but the advantage is that um, you can do melt spinning of this fiber at a much lower temperature compared to the other types of fibers. The more common one is like 610 and 720. The 440s, 550 and 650 are not as common. So these are all based on alumina silica precursors, and you get very highly fine diameter type of process. Okay. So these are the properties, some of the properties of the Nextel 610 fiber. So it contains alumina, some small amounts of silica, and small amounts of ammonia. Sorry, iron oxide. So what are the advantages of some of these fibers? So if you silicon carbide, for example, if you have a component that is undergoing creep or fatigue, these materials are pretty high uh, resistance to creep type of failure processes. So can you compare the properties of all these fibers in one single slide, one single bar chart? Yes, you can. So if you put all these things, you can see that carbon fibers are pretty good as far as Young's modulus and the tensile strength combinations, etc. So this is a repeat of the earlier homework. So this is still homework 1, but I would like you to do homework 2, where you are looking at the different types of carbon, alumina, and silicon carbide fibers and how they are manufactured. Just give me one paragraph each. Who are the manufacturers and what are the fiber properties? And and if you can, just call up the fiber manufacturer and get an approximate cost depending upon the volume. So give me a cost based on, like, for a specific uh, area or volume or weight or whatever, and please give me those numbers on the D2L as a PDF file. Okay, so I think I posted these papers on ceramic toughening theories, and I will also be posting a paper by a person called Anthony Evans. He presented a, a fantastic paper at the American Ceramic Society conference. It used to be in Cocoa Beach in every January. In fact, it'll be going on starting this Sunday, and his paper was probably the one that was attended by the largest number of people in that conference. I mean, like, almost 600, 700 people attended his talk. So everybody was interested in that. I mean, um, Aveston, Kelly, and Cooper developed the theories behind composites, but Tony Evans is the one who discussed and told us for the first time about the effect of the interface in a ceramic composite. So we are eternally grateful. Unfortunately, he passed away a couple of years ago due to cancer. In fact, many of our famous ceramists and composites people have died recently. We don't know exactly for what reason, but anyway, I mean, we are really grateful to him for having tried to explain the properties of these composites um, for the use of a lot of us. Okay, so that ends this lecture, and I will cover the other lectures in the future classes.